Part two of our lecture is about the transformation of data from one dimension to another dimension. And in this example, we're transforming linear data of tracks of tornadoes into hex bins, and I'll discuss the reason why we use hex bins as our container which we're transforming our data into. So when we talk about the transformation of data, the first place to start is we should draw a distinction between discrete and continuous data. So discrete data is separate, distinct values or categories that have distinctive gaps in between. So this is typically represented as whole numbers, and the key to discrete data is that it is counted. So you can't take values in between those, but rather you use whole numbers. So this could be a count of a material, for instance, or it could be the ranking of the impact of something, right? As long as those are whole numbers that are counted. Whereas continuous data is a numerical value that can exist within a given range, and it's measured with various levels of precision, and it allows for meaningful mathematical operations. So often we use continuous data. We think about there's a range of possible values, say like distances or feet within a mile, and then we can measure that to various levels of fractional precision. So if we think about different landscapes, for instance, we can think about the different types of discrete and different types of continuous data that we would find within within a landscape. So here is poultry farms in Appalachia, and in this we could say, what's discrete data? Well, the number of poultry sheds, for instance, we could count at any given site. The number of facilities themselves, 1, 2, 3, 4, for instance. So those would be discrete sets of data. If we were to take continuous data, we could say what is the average distance between sites to each other. So what is, what are all these distances and what's the average of them? That'd be a continuous data. Or what is the area of these waste pools? Those would be continuous data as well. Similarly, if we were to look at like the Albuquerque Balloon Festival landscape, we could see a set of discrete and continuous data within this as well. Discrete data could be the number of balloons, right? The number of people that attend the festival. Continuous data could be height balloon is above the ground, circumference or height of each balloon itself, etc. So, a pretty easy distinction, but it's important to keep in mind whenever you're looking at a landscape, whenever you're trying to transform that landscape or that geographic phenomenon into your map, think about what is discrete and what is continuous data within that landscape or that data frame. I'm looking at a map view. We say, what's discrete data? Discrete data are all these individual geothermal locations, right? And then continuous data could be the raster field that's interpolated from all the known points, right? And so this level of favorability for geothermal, enhanced geothermal systems, for instance, that raster has this color gradient that is continuous data because it's showing values across the entire surface of the country. The discrete points, right? These are discrete points, discrete XY points. So one of the complicating factors that we have is that we have both discrete and continuous data, and we have discrete and continuous geographic space. And they're mostly related, but there are some distinctions to draw out. So discrete geographic space refers to the type of space that is composed of distinct, separate, and non-overlapping entities or regions. So we could think of this as a set of points, or a set of cells, or a set of polygons, often administrative polygons, that have well-defined boundaries. So counties, for instance, are discrete geographic spaces because they're individual, they're non-overlapping, and they're separate from each other. Same with XY data points as seen before with the geothermal sites. So this is an example of discrete data or discrete geographic space. We have the United States. All of them have defined non-overlapping boundaries. Whereas continuous geographic space refers to the type of space that is uninterrupted or unpartitioned by bounded units. So we typically think of this as smooth variations of physical and environmental features, such as elevation, temperature, precipitation, etc. And those values do not change abruptly at administrative boundaries, but rather they have kind of a smooth gradient transition that is independent of state boundaries or county boundaries, for instance. So elevation is a continuous geographic surface, right? That is not contingent on the container that it's within. So here's an example of vegetation or precipitation or some sort of geographic data. Elevation, I think it's elevation. You can see how it's not beholden to the administrative boundaries of different countries, but rather flows continuously across the entire land surface. Yeah, this is elevation. So same here, we have these oceanic currents, right? And these are continuous geographic spaces, right? They're not partitioned off into particular containers. And so oftentimes what we have to do is transform data, spatial data, from one dimension, from its continuous or discrete dimension, into a new dimension. And this is explicitly for particular map purposes. And there's 4 different types of cartographic transformations. That is interpolation, classification, raster math or raster calculators, and aggregation. And what we're doing with our lab this week, part 2, is an aggregation transformation. But I'll go through all 4 just so there's some clarity about what each of these ones are. So when we're thinking about how we're going to transform discrete data into a continuous surface, that is typically what's known as a process of interpolation. So interpolation is a spatial analyst technique where we estimate values at unobserved locations within a geographic area based on a collection of known data points. So this allows us to see a continuous surface based on a sample. So if we have a bunch of sample points of elevation, for instance, all these x's are sample points, then we can use various types of interpolation methods within our ArcGIS toolbox. There's inverse distance weighting, there's kriging, there's, what's the other one? No, those are the 2 most common: inverse distance weighting, IDW, kriging. And what that can do is it can take a bunch of known sample points and then find the estimated value based on different weighting parameters of what the cell would be based on known cells, and then create a surface from that. And so we often use spline. That's the other one, spline. We often use this technique in order to take a bunch of samples out in the field, soil samples, vegetation samples, wildlife samples, whatever that kind of like natural phenomena that we're sampling is, and then within our study area create a surface so we can estimate or understand what the likelihood is of that distribution across the whole surface based on a set of known points. So that is the process of interpolation. We also have the process of classification, and that is the categorizing and mapping of various types of surfaces, typically based on remotely sensed data. So that's we're taking a imagery that has a continuous data set, and we're creating land cover classes from that based on some sort of pixel value. And then from that we can say, here are the different types of land cover types, and we can transform that into discrete data. something that you do often in remote sensing classes, so I'm not going to go into a bunch of detail here about that process, but something that we often do is uh, the transformation of continuous data into discrete geographic spaces, or the classification process. And all of you that have taken remote sensing are aware of the different kind of processes, different scales, different types of um, classification metrics that are used. Okay, and then raster math is a computational process for performing mathematical operations on pixel values of one or more raster data set, which enables various types of spatial analysis and modeling through different algebraic and logical functions. And so this is really the transformation of continuous data into other continuous spatial dimensions. So for instance, and we'll do this a little bit later in the term, we'll take a digital elevation model, we'll use a logical function on that and transform that digital elevation model into a shaded relief that mimics the shadows and illumination that you would get from a sun hitting a landscape in order to show kind of a three-dimensional texture. We'll talk more about this later in the semester, but that is a transformation of one set of continuous data into a new continuous surface. Often we use this in our different ecological and habitat and site suitability modeling, right? We have a bunch of different sets of raster and raster derivatives, some different classifications within that, and we use some different raster math and some different weighting techniques in order to combine those to create new site suitability models that allow us to see how all these different layers stack up next to each other. Okay, so those are all ones that we do in different types of GIS operations and classes, remote sensing, modeling, etc. The one that we use often in cartography, and specifically for this lab, is aggregation. And that is the process of combining and summarizing spatial data from one either coarser or from simplifying and summarizing spatial data from one geographic scale into a different geographic scale. Often in that process we're simplifying or reducing the detail and taking a large number and kind of compacting it into smaller areas. So for instance, we might have a bunch of residential points within census blocks, right? And what we want to do is perform a count of how many residential units are in each census block, and then create a map that has that weighted count or demonstrates that count in various ways. And one thing that we get into within this aggregation process is what's known as the modifiable aerial unit problem. And this refers to the issue in spatial analysis where the result of the analysis is dependent on the shape and the size of the polygon units that the data is aggregated into. And so this can potentially lead to biased or inconsistent conclusions, because depending on what the shape or what is the administrative unit that we're aggregating our discrete data into, right? Back in this example, these are census blocks, but if we were to change the size or the shape of these census blocks, say we use neighborhood boundaries or census tracts or whatever those different boundaries were, then these patterns and these counts would vary based on those distributions. And that's known as the modifiable area unit problem. And that's really a problem of scale and a problem of shape. So in the problem of scale, it's like how big are the units that we're aggregating our data into, right? And that size of the unit can change what the pattern emerges, right? So here's an example of some points being aggregated into large blocks, and that gives us one type of pattern. we aggregate that exact same data into smaller pieces, and that gives us a very different looking pattern, right? From this map here, or this set of maps here, that depending on the size of the units that's drawn, that changes the pattern of the data that we're seeing. So in this case, this is percent of population under 5. When drawn at the census tract level, that produces one type of pattern. When drawn at the county level, that produces another pattern. So the size of the unit, the scale of the unit that we use to aggregate our data into, can change the appearance of that data. So that's the problem of scale. We also have the problem of aggregation and the problem of size. And in that case, that is saying that the shape of the problem of aggregation is the same as the problem of shape. The shape of the bounded area that we're drawing can influence the pattern as well. So not only the scale, but also the shape. And so in this example, we can see these two schematics of different political affiliations. So blue Democrat, red Republican, and 4 districts here. Depending on how that is drawn, right, we can make that so the end result is a pattern of 3 red districts and 1 blue, or 3 blue districts and 1 red, with the exact same data just based on how we're drawing those bounded areas out. So this is what's known as the process of gerrymandering in political science. And in that process, there is much debate about, who draws maps, what are the rationales and the power structures of what the people that are drawing the maps and validating those map drawing results, what are they trying to ensure, how are they politically motivated, etc. So we can see, from this example, if we have a population that's 60% orange and 40% purple, depending on how we draw that, that's going to give us 3 orange and 2 purple districts pretty easily. We could also draw that in a way that would overrepresent the orange, or in a way that would overrepresent the purple based on the shape of those different districts. North Carolina has been a prominent example of this. North Carolina is, in actuality, a pretty kind of 50-50 split between Republican and Democratic voters. But the way that the congressional districts are drawn starting in 2012 really is done intentionally to maximize the representation of Republicans within the district and minimize the representation of Democrats within the state congressional districts. And you can see by the shape of these congressional districts that they're really drawn with a high level of specificity and precision in order to ensure those results, right? And so that's one issue of aggregation and how it can be manipulated for very particular political purposes. And it should be noted too that all political boundaries are drawn by people, and all people have biases. And if you're in a position to draw those boundaries, like, you achieve that position through particular political avenues. And with those political avenues comes conditions and biases that are kind of embedded within that. And so one way that we as cartographers can circumvent those kind of political trappings is to use what's known as a hex bin aggregation technique. And what the hex bin technique does, and this is what we'll do for our lab, is it puts a hexagonal mesh set of polygons on top of our data set. And so that way, when we're aggregating our data into it, the aggregated units are not what the pattern that emerges is not beholden to pre-existing political boundaries, but instead we're going to get this equal size grid that will allow us to see the pattern a little bit more clearly. So this actually came from a cartographer from Michigan State who now works for ESPN, who took basketball data and took where people were taking jump shots at particular times, and then measured the accuracy and the frequency of those field goal attempts. So here's LeBron James, for example. This is back in 2014 that he first did this. Basically saying, like, here's all this different discrete data of where LeBron James shoots the ball from at various times, and each of those different data points have a efficiency value, like how often, if it's a make or a miss. And so you can aggregate that data, and um, instead of using like these zones that were pre-existing on the basketball court, we're going to put this hexagonal mesh on top of it, so we can really see, what areas of the court this particular player is efficient from, shoots frequently from, is inefficient, and we can size those bins to represent the frequency as well. So down here, these large bins that are red basically says that this player, LeBron James, shoots often. This was 10 years ago, by the way, as well. Shoots often from this location and scores at a higher than average rate. Whereas up here from the right wing, he shoots fairly often, right, because they're large size hex bins, but is not very efficient. And so that's a technique he came up with, Kirk Goldsberry came up with, that demonstrated, how you use this hexagonal mesh network in order to aggregate a bunch of point data and turn it into a polygon pattern. And we use this now often for urban data in particular. We look at things like crime, look at things like traffic incidences, look at things like social media posts, and we aggregate all that individual point data into these bins. And in the process of doing so, that allows us to see it's kind of like a heat map that we made in the previous lab with the rats, but with a little bit more kind of like analytical function than the heat map gives you. The hex bin technique is that we can also do this with line data, right? So we can take, here's airplane paths that are coming into O'Hare Airport, and from this we can see, the frequency of how often the airplanes are going over particular parts of the Midwest. So we can take line data, and oftentimes we have, like we looked earlier with the pipeline data, we have all this linear data that overlaps itself. That's kind of hard to read, and we can take that, we can aggregate those into bins, into hexagonal bins, and that allows us to see the pattern of those of that complex overlapping linear network, and a little bit more clarity and a little bit more analytical robustness. So the first thing that you should do is, there's a video that John Nelson did that explains this technique specifically with the airline data, and he goes through how he made this representation explicitly. So that's in your lab instructions. Go through that first, and then what we'll do from there is transform tornado track data that you download and that you clip by a particular state. So here's tornadoes for the state of Nebraska, for instance. We'll take that and we'll aggregate those into a hexagonal mesh network, and that'll give us a result of the frequency and intensity of different tornadoes in a state. So here's some examples from previous labs. And here is a student that was able to highlight the intensity and the frequency of tornadoes in Missouri. And here's another one for Alabama. Right? And then through this process, we're taking, all these overlapping lines of data, and we're throwing them into this hexagonal network. So the instructions go through the process of doing so, how to size and symbolize these hex bins, and then, you have to figure out a process as well, how to make that into a legend. That's kind of the hardest part, is how are you going to take this bivariate hexagonal data and make that into a legend. So it's kind of a challenge technique for that one. But here's a good example from last semester that demonstrates, how this technique can be used, and how from that you can see that, through that kind of complex set of line data, you can see that, our highest frequency and our highest intensity tornadoes in Alabama, exist in this kind of one region. Other parts have less frequent and less intense earthquakes as a whole. So that is linear data and an introduction to your two labs this week.